Да, именно паузу сразу не нажимать. Она сейчас работает, и в самом конце. Не, сейчас будет пара. Сейчас будет пара, но она тоже будет. Они сами. Да, если беру все, почему можете выключить? Не, сейчас сюда раз.
То есть это не страшно, что там будет частота, да? Потом ты
Ну вот уже появилось. Да. Тут, короче, трансляция. И...
Я не слышал первую часть фразы, я только что вырубил наушники.
Ага. Тут, короче, я в трансляцию включил. Вот здесь Pirkovskii здесь уже говорится сигнал. Он уже, в принципе,
Если он так разбирается, то...
не, как бы здесь, если что, то тут очень все просто. Кто пишет с одной стороны так, другой пишется вот так, дальше вот так. Стирается все вот так, просто вектор. Можно просто все очистить, либо можно сделать новую страничку и потом перевести в вот дальше это уж как-то. Еще тут фигурки надо надумать. Главное, чтобы не пошли в 110. Вот это самое главное. Ну, главное, чтобы 110 не пошли.
Ну, в расписании написано.
Ну, если написано, просто можем помнить, что в прошлый раз было 110, потом. Ну, я не знаю, я честно. Как все сделал.
О, вот ты прям унизил.
Дима, где у нас?
Куда пойдешь?
А я не понял.
Кстати, сам Pirkovskii не смотрел расписание.
Здрасте. Так, очередная комната, да? В связи будем, да?
Ну, в расписании написано так.
Интересное кино. Как все это... Я, честно говоря, как не очень люблю вот эту штуку писать. Ну ладно. Сейчас ничего менять не будем, а вообще как-то...
Скорее всего, это связано с тем, что здесь записывают для чувства.
Ладно.
А можно короткий вопрос по задаче?
Конечно.
Там была C бесконечность на многообразие. Вот, разумно брать компакты, которые попадают просто в карту?
Можно, но можно сделать поэлегантнее, так, чтобы координаты не используются. И компакт производные тогда.
Ладно.
Так тоже можно. Как вы предлагаете, но можно и без этого дела. Ладно, попробую с раскройкой разобраться. Если, честно говоря, ну ладно, если, в общем, не критично, я все-таки, наверное, прошу, чтобы нас обратно в нормальную аудиторию вернули. Честно говоря, немножко побаиваюсь. Так, Настя. Так, я вот сюда должен нажимать, нет? Неизвестно. Руководителя записи нету. Ладно, я нажму старт. Проверим. Пошла трансляция. Если в эфире. Вот. Pirkovskii залез. Okay, so in the previous lecture we discussed a convenient way of topologizing a vector space by means of families of semi-norms. So let's recall the construction. So we start with fully normed space that is a pair consisting of vector space X and a family of semi-norms P on X. And we consider the topology of P generated by this family. This is the topology whose subbase consists of all balls of the following form. If P little p rounds over our family, epsilon rounds over positive numbers, and if little x rounds over x, then the resulting family of balls is a subbase of a certain topology, and this topology is called the topology generated by P. So a polynomial space becomes a topological space, and it turns out that the algebraic operations are continuous, so we get a topological vector space. And our first goal for today is to give a geometric characterization of such spaces, that is, of those topological vector spaces whose topology can be given by a family of semi-norms. At the end of the previous lecture, we introduced the main technical tool for this characterization, namely the Pirkovskii functional. So let's recall the definition. Suppose that X is a vector space and S is an absorbing subset. Absorbing subset of X. This means that for every point little x, this point belongs to lambda S if lambda is big enough. So S absorbs every point. The Minkowski functional, Ps, is a function, a non-negative function on X, given by the following formula. This is the infinity of those non-negative lambda for which X belongs to lambda S. This is the Minkowski functional. We proved that if S is not only absorbing but is also absolutely convex, then the Minkowski functional is a semi-norm. And moreover, we have the following two inclusions. The open unit ball corresponding to this semi-norm is contained in S, and S is contained in the closed unit ball for this semi-norm. So this was proved at the end of the previous lecture. By the way, here is a useful example, which I forgot to tell you about at the previous lecture. If we start with a semi-norm, Q. If Q is a semi-norm in our space, then we can take the open unit ball corresponding to Q, and it's an absorbing absolutely convex set. It turns out that the Minkowski functional of the open unit ball of Q, as well as the Minkowski functional of the closed unit ball corresponding to Q, are equal to Q, to the original semi-norm Q. Okay, so what we are going to do now is to show that a topological vector space is polynormable in the sense that its topology can be given by a family of semi-norms, even though it is locally convex. Locally convex spaces. So before defining locally convex spaces, let's recall some definitions from general topology. So we suppose that X is a topological space, and little x is a point in our space. By definition, a neighborhood of X is, well, and at this point you might think that I'm a bit crazy, because of course everyone knows what a neighborhood is. But I'm going to give you a slightly modified definition of a neighborhood, which is not entirely standard. Well, at least it is not a standard for the Russian-Soviet mathematical school. So by a neighborhood of a point, we mean a set, a subset U of X, such that little x sits in the interior of U. In other words, this means that there exists an open set V such that X belongs to V and V is contained in U. So the point is that a neighborhood is not assumed to be open. U itself is not necessarily open. We only require that little x sits in the interior of U. This generalized concept of neighborhood is due to Fréchet, And it was later observed by Dieron and Schwartz in the 1940s that this definition is especially useful for the theory of topological vector spaces. So we will follow this definition of a neighborhood.
So we'll call the normal neighborhood open neighborhood.
Yeah. Definition 2, we will have a family beta x of neighborhoods of little x. Then we say that B is a base of neighborhoods of f of x, a base of neighborhoods of x, or briefly just a base at x. If for every neighborhood U of x, there is a neighborhood V in this family such that V is contained in U. This is more or less standard definition. For example, if we have a metric space, then the family of all balls with a fixed center is the base of neighborhoods of this point. And finally, we say that a family sigma x sigma x of neighborhoods of x is a subbase at x. If the family of all finite intersections, so U1 to Vn, of elements of sigma x is a base at x. Okay, so now let's suppose that we have a polynomial space, and let's introduce some notation. Suppose that x is a polynomial space equipped with a family of seminomials P, and for every element level x in our space, for every finite family P1 to Pn of seminorms in our family, and for each positive epsilon, we consider the following set as denoted by U P1 to Pn epsilon of x. So this is just the intersection of the respective open balls corresponding to the seminorms Pi of radius epsilon from 1 to n. So explicitly, this is the set of values y for which the following inequality holds for every I from 1 to n. And we have the following simple proposition. First of all, if we consider all open balls centered at x and corresponding to all seminorms in P, then this is a subbase of neighborhoods of x. And second, if we consider such finite intersections, U P1 Pn epsilon of x, again P1 to Pn are in our family, and epsilon is positive, and this is a base of neighborhoods of x, a base at x. This is almost trivial if we recall the definition of the topology. The only point which is maybe not immediate from the definition, but is still very easy, is that oops. Yes. Okay. Formally, to get a subbase of neighborhoods of X, we must take this subbase of the topology, that is the family of all open balls with arbitrary centers, and consider those of them which contain little x. This is what is immediate from the definition. The point is that x is not necessarily in the center. But by using the triangle inequality, we can easily find a smaller ball centered at x and contained in the bigger ball. And that is why we consider here only those balls whose center is exactly x. Oh, this is. So the details are, I'll leave the details as an exercise for you. Okay, let's now observe that each set of this form is convex. And moreover, if x is 0, then this set is absolutely convex. This is more or less immediate from the triangle inequality. Of course, it's enough to consider only balls corresponding to a single semi-norm, because the intersection of convex sets is convex, and the intersection of absolutely convex sets is absolutely convex. And the triangle inequality, again, also it suffices to consider only the case where x is 0, because the translation of a convex set is convex. And finally, the axioms of a semi-norm easily imply that every open ball centered at 0 is an absolutely convex set. And now we give our main definition. We say that a topological vector space X is locally convex. Locally convex if X has a base of neighborhoods of 0 consisting of convex sets. And a standard variation for locally convex topological vector spaces. So we variate them as follows, and we call them just locally convex spaces. So by definition, a locally convex space is the same as a locally convex topological vector space. And we abbreviate them as LCS. Let's observe that if we consider only open neighborhoods of 0 here, then we get an equivalent definition. This easily follows from the following simple exercise. If X is a topological vector space and S is a convex set, then the interior of S is also convex. This is true in any topological vector space. So, as a result, probably from this exercise, we see that the topological vector space X is locally convex, even only if it has a base of open neighborhoods of 0, consisting of convex sets. Well, indeed, if we have a base of neighborhoods of 0 consisting of convex sets, then we can just replace each set in this family by its interior, and we get a base of open neighborhoods of 0, which are still convex. Okay. Well, actually, we already have a concrete example. We look at this observation, and we conclude that if we start with a learned space, XP is the learned space, then X equipped with the topology generated by P is a locally convex space. And it turns out that this example actually describes all locally convex spaces. So we have the following theorem. Topological vector space X with topology 2 is locally convex, even only if there exists a family of semi-norms, a family P of semi-norms on X such that 2 is generated by P. So in other words, we can say that topological vector space is polynormable if and only if it is locally convex. Let's give the following definition. Any such family P, is a defining family. Of semi-norms on X. Of course, there are many such families, and we discuss this phenomenon later, but at this point it's more or less obvious. If we take any defining family and say multiply each semi-norm from this family by 2, then we still get a defining family. Okay, let's try to prove this result. We start with the following lemma. First of all, I claim that if X is any topological vector space, then each neighborhood of 0 contains a circled neighborhood of 0. Contains a circled neighborhood of 0. And second, if X is a locally convex space, then each neighborhood of 0 contains an absolutely convex neighborhood of 0. Well, why is it so? First, part 1. Let's recall that the multiplication by numbers is continuous. So, the multiplication is continuous. So, if we denote by D, D bar, the closed disk, well, it will be disk if the base field is the field of complex numbers, and this is just a closed interval from -1 to 1 if the base field is the field of real numbers. So if we denote it by D bar, then the continuity of this map implies that there exists another neighborhood of 0, say V, such that D multiplied by V is contained in U. Well, indeed, formally, the continuity of this map implies that we can find the neighborhood of 0 here and the neighborhood of 0 here, such that their product is contained in U. And if the neighborhood, which is in K, contains the disk of radius epsilon, then we just multiply the second neighborhood here by epsilon, and we, in this way, we can replace this epsilon neighborhood here by the neighborhood of radius 1 by D. So this follows from the continuity of the multiplication. And now we let W denote dV, and we see that W is a circled neighborhood of 0, which is contained in U. Circled, and it is contained in U. So this completes the proof of part 1. And to prove part 2, first of all, since X is locally convex, now we may assume that U is convex, because every neighborhood of 0 contains a convex neighborhood of 0. So here we assume that U is convex. We already know that there is a circle neighborhood of 0 contained in U. There is a circle neighborhood of 0, W, such that W is contained in U. And now let's just take the convex hull. Let W prime be the convex hull of W. Then W prime is absolutely convex. Well, indeed, it's convex by construction. And let's also recall from the previous lecture that the convex hull of a circled set is circled. So W is circled, so W prime is also circled, and this means that W prime is absolutely convex. And it is still contained in U, because U was assumed to be convex. And this completes the proof. So as a corollary, we get one more equivalent definition of a locally convex space, namely a topological vector space X is locally convex if and only if it has a base of absolutely convex, a base of neighborhoods of 0, neighborhoods of 0, consisting of absolutely convex sets. This is immediate from part 2. So we first we take a basic neighborhood of 0 consisting of convex sets, and then we replace each of them by a suitable absolutely convex neighborhood of 0. And again, we can replace here neighborhoods by open neighborhoods, and we still get the equivalent definition. Okay, now let's prove our theorem. Clearly, we already know that every if our topology is generated by a family of seminorms, then it is locally convex. So we must prove the converse. So suppose that we start with a locally convex space X, And we choose a base of neighborhoods of 0 consisting of absolutely convex sets. Let beta be a base of neighborhoods of 0 consisting of absolutely convex sets. And we define a family of seminorms P as follows, for which for each neighborhood in beta we take the respective Minkowski function PV, where V runs over beta. So this is a family of seminorms. I claim that P generates the original topology too. Well, indeed, why is it so? We already know that for every V in beta, we have the following inclusion. So the open unit ball corresponding to PV is contained in V, and this is contained in the respective closed unit ball, which is in turn contained in the open unit ball of radius 2. And now let's consider the first inclusion. UPV is contained in V, and let's observe that this inclusion implies that the map from X equipped with the topology 2 of P to X equipped with the topology 2, and this is basically the identity map. It takes every element to itself. This map is continuous. Well, indeed, it is continuous. This inclusion means exactly that this map is continuous at 0. So for every neighborhood of 0, we can find a neighborhood of 0 here, such that this inclusion holds. But a linear map is continuous at 0 if and only if it is continuous. So it is continuous. And the second inclusion, well, let's modify it. Modify it slightly. We multiply everything by epsilon over 2, and we get the following. Well, now this is a sub-basic neighborhood of 0 in tau of P. So the standard sub-base of neighborhoods of 0 in tau of P consists exactly of such balls. And this is the neighborhood of 0 is topology 2. So this inclusion implies that the same map which acts in the opposite direction from x2 to x2 of P is continuous. So if we combine these two facts, we conclude that the topologies are the same. And this completes the proof. Okay, so as a result, we see that polynomial spaces are related to locally convex spaces in about the same way as metric spaces are related to meteorizable topological spaces. So in other words, of course, the structure of a polynomial space is richer than the structure of the respective locally convex space. In other words, a locally convex topology can be generated by many different families of seminorms. But in practice, when we work with locally convex spaces, the concrete family of seminorms is usually not so important. And what is really important is the topology generated by this family. And probably that is the reason why the notion of a polynomial space is not so much in use. And on the other hand, the notion of a locally convex space is absolutely common and standard. So I will follow the tradition, and I will never use the notion of a polynomial space anymore. But of course, the fact that every locally convex space is polynormable, that is the theorem, it is really very important, and we'll constantly use it. Okay. So our next goal will to give a useful continuity criterion for linear operator. Continuity criterion for linear operators. Between locally complex spaces. Well, here the motivation comes from the following standard fact of functional analysis. You have two normed spaces x and y, and the linear operator t from x to y. Then it's a standard fact that t is continuous, even only if it is bounded in the sense that there exists a negative constant c, such that for every little x and x, the following inequality holds. So what we are going to do is to extend this result to locally complex spaces. Okay, so let's start with some notation and some terminology. So suppose that X is a vector space. So at this point, we don't assume that X is equal to the topology. It's just a vector space. And suppose we have two seminorms, P and Q. Two seminorms on X. We say that Q is dominated by P. And write the following symbol. If there exists a constant c, a negative constant c, such that the following inequality holds for every x. So Q is dominated by P is Q is less than or equal to P up to multiplicative constant. By the way, maybe you remember that in the previous lecture we used the same symbol to denote the absorption relation for subsets of a vector space. And in fact, this is not a coincidence. We have the following simple proposition. Part 1, Q is less than or equal to P if and only if the unit ball corresponding to P is contained in the unit ball corresponding to Q. And part 2, Q is dominated by P if and only if UP is absorbed by UQ. The proof is a simple exercise for you. Actually, 2 readily follows from 1, and the left to right implication on 1 is immediate. The only part which is not entirely immediate is to prove the right to left implication. That is, if UP is contained in UQ, then Q is less than or equal to P. This is not immediate, but this is, I hope this is still very easy. So this is an exercise. Okay. Well, some more notation. If we have two seminorms P and Q, then we can take their pointwise maximum. So this is a function from x to the non-negative numbers, which is just the pointwise maximum of two numbers P of x and Q of x. And it's a very simple observation that this is also a seminorm. The maximum of two seminorms is a seminorm. And the open unit ball corresponding to this maximum is just the intersection of the unit balls corresponding to P and Q. This is immediate from the definition. Right? The maximum of two numbers is less than 1, even if each of them is less than 1. Okay, so a useful intermediate step towards our goal. So we want to prove the continuity criterion for a linear operator between local electron spaces. But a useful intermediate step is to prove a continuity criterion for a seminorm on a topological vector space. So we have the following result. Theorem. Suppose that X is a topological vector space and Q is a seminorm of X. And then the following conditions are equivalent. Condition 1, Q is continuous. Condition 2, Q is continuous at 0. Condition 3, the open unit ball corresponding to Q is open in the topology 2. And condition 4, UQ is a neighborhood of 0. Again in topology 2. So these conditions are equivalent, and moreover, if our space is locally convex, if X is locally convex, and if P is a defined family of seminorms, of X, then the above conditions, 1, 2, 4, are equivalent to condition 5, which is as follows. There exist finitely many seminorms on P, P1 to Pn, such that Q is dominated by their maximum. Okay, let's prove this result. Clearly 1 implies 3. And 3 implies 4. Well, this is clear because UQ is the preimage of the interval from 0 to 1, the half interval from 0 to 1, including 0, the preimage of an open set is open, if Q is continuous. So 1 implies 3, 3 implies 4, of course. Let's now show that 4 implies 2. 4 implies 2. Well, since UQ is a neighborhood of 0, well, clearly we have the following conclusion. Q of UQ is contained in the interval from -1 to, well, from 0 to 7. Oh, sorry. It is contained in the interval from 0 to 1, including 0. If we multiply everything by epsilon, this implies that it takes epsilon multiplied by uq to the interval from 0 to epsilon. But if we multiply the neighborhood of 0 by a positive number, we still get a neighborhood of 0. And since epsilon is arbitrary, we conclude that Q is continuous at 0. And now to complete the proof of the equivalence between 1, 2, 3, and 4, we have to show that 2 implies 1. 2 implies 1. So we assume that Q is continuous at 0, and we want to show that it is continuous. Okay, so we know that for each positive epsilon, there is a neighborhood of 0 u, such that Q of u is contained in the interval from 0 to epsilon. And we will show that Q is continuous at any other point. And indeed, for every point little x in our space, little x plus u is clearly a neighborhood of x. This is a neighborhood of x. And if we now take an arbitrary point y in this neighborhood, belonging to x plus u, and try to estimate the difference between the distance between q of y and q of x. So this, by the triangle inequality, we can estimate this as q of y minus x. And y minus x sits in u. So because of this, we see that this is smaller than epsilon. And this inequality readily implies that Q is continuous at x. So Q is continuous at every point, so it is a continuous map on x. Okay, and finally, we now assume that x is locally convex. We'll take a defining family of semi-norms, and we want to show that, for example, 4 is equivalent to 5. So now assume that P is a defining family of semi-norms. So we want to show that UQ is a neighborhood of 0 if and only if condition 5 holds. Okay, so UQ is a neighborhood of 0 if and only if it contains a basic neighborhood of 0. This means that there exists a positive epsilon, and there exist finite remaining semi-norms P1 to Pn in our family, such that UQ contains the basic open neighborhood of 0, U, P1, Pn, epsilon of 0. Okay, this neighborhood can be written in the following way. This is U, P epsilon of 0, where P is just the maximum of Pi from 1 to n. And this is the opening ball corresponding to the semi-norm P divided by epsilon. P over epsilon. So we see that UQ contains P over epsilon, but we already know that this containment is equivalent to the following inequality. This holds if and only if Q is less than or equal to P over epsilon. So for each policy of epsilon, there exists finite many seminorms P1 to the n, such that Q is less than or equal to a constant times the maximum of these seminorms. But this is exactly our condition 5. Okay, so this completes the proof.
Какая-то магия, как будто мы в одну сторону только проверили.
Чего одно?
Не знаю.
Вроде,
Вроде да.
We don't have the statement here. I'm sorry, I had to erase the statement. But for means that Q is a neighborhood of 0. And the set is a neighborhood of 0 if and only if it contains a basic neighborhood of 0. So this is just this equivalence. And this equivalent is equivalent to this inequality. So I hope this is correct. Okay. Let's introduce the following notation. It will be useful in these situations. Let's denote by Sn of x the set of all continuous seminorms in x. This definition makes sense for every topological vector space. So as a corollary, we see that if X is a locally convex space and P is a defined family of seminorms of X, then first of all, every seminorm from P is continuous. This is immediate from our previous theorem. For example, because it's open in the ball, it is indeed open in the original topology. This is equal to the continuity of our seminorm. And condition 2 is that, sorry, not condition, part 2 is that Sn of x is the largest defining family of seminorms. Of seminorms on X. Well, indeed, well, P is contained in Sn of x, so if we introduce a new topology on X generated by this bigger family, it could be stronger than the initial topology. But actually it will be the same because all basic sub-basic sets from here, that is the spectrum balls, are open in the original topology by the previous theorem. So we see that the topologies are the same. So Sn of x is indeed a defining family of seminorms, and it is the largest family, defining family of seminorms because of this inclusion. Okay. Okay, now we are ready to prove the continuity criterion for a linear operator theorem. Suppose we have two locally convex spaces, X and Y. P is a defining family of seminorms on X, and Q is a defining family of seminorms on Y. And suppose that T is a linear operator from X to Y. And the following conditions are equivalent. Condition 1, T is continuous. Condition 2, for every seminorm Q in big Q, Q composed with T, well, this is a map from X to the non-negative numbers. This map is continuous. And condition 3, for every Q in the second family, there exists a constant C, non-negative constant C, and there exist finitely many seminorms from P, P1 to the N. such that for every x in X, we have the following inequality. Q of T of X is less than or equal to C times the maximum of Pi of X. From 1 to So let's observe that in the case of normed spaces, condition 3 means exactly that T is bounded. So there exists a constant C such that for every x, the norm of T of X is less than or equal to C multiplied by the norm of X. So this criterion generalizes the well-known fact from functional analysis that the operator between normed spaces is continuous if and only if it is bounded. Okay, well, why is it so? First of all, let's observe that this map Q composed with T is a semi-norm of X. If you compose a linear operator with a semi-norm, we get a semi-norm. And now conditions 2 and 3 are equivalent by the previous theorem. So we just apply the previous theorem to this semi-norm. This shows that 2 and 3 are equivalent. Just apply the previous theorem to Q composed with T. Okay. And now we want to show that 1 is equivalent to 2. Clearly, 1 implies 2. Because Q is continuous. The composition of two continuous maps is continuous. And finally, we have to show that 2 implies 1. Well, Q composed with T is a semi-norm. So again, we apply the previous theorem, and we conclude that the unit wall corresponding to this semi-norm is open. But let's now observe that this is nothing but the pre-image of UQ under T. So the set consists of those x for which Q of T of X is less than 1. That is, T of X sits in UQ. So this set is open. But this is almost the continuity at 0. For order to get continuity at 0, we must take an arbitrary positive epsilon. And observe that this set is also open. Just by linearity. And that's it. So since UQ epsilon belongs to the standard subbase of neighborhoods of 0 in Y, we see that the preimage of any such neighborhood of 0, any such subbasic neighborhood of 0, is a neighborhood of 0 in X. So this means exactly that T is continuous at 0. But for linear maps, continuities at 0 is equivalent to the continuity. T is continuous. And this completes the proof. Okay. Okay, probably now we're ready to answer the question why locally convex spaces are better than general topological spaces. Well, we already know about one of the advantages of locally convex spaces, Namely, when we work with locally complex spaces, we have two more or less equivalent languages: the language of neighborhoods, the language of general topology, and the language of seminoids. And this is very convenient. But on the other hand, the language of seminoids, well, it is convenient, but it's just a convenient user interface. So every statement which about local complex spaces, which is made in the language of seminorms, can be translated into the equivalent language of neighborhoods of zero. And the real advantage of locally complex spaces within the class of all topological vector spaces is that on each Hausdorff locally complex space, there exists sufficiently many continuous linear functions. Continuous linear functionals separate the points. This fact is proved in much the same way as in the case of normal spaces. Well, indeed, to begin with, let's observe the following fact, that if we start with a locally complex space X, with a defined family of seminoids P, and if X0 is a vector subspace of X, then the topology on X0 is deduced from X is also clearly locally complex, and it is generated by the restrictions of seminorms from family BP to X0. Not P, not to P. Again, this is formally not immediate from the definition, but again, this is immediate from triangle inequality, because formally we must take all open balls in X and consider their intersections with X0, and such intersections form a subbase of the topology on X0 induced from X. But again, every ball which contains a point in X0 contains a smaller ball centered at this point. We have already used this picture today, and the same picture shows that the induced topology is generated by all such seminorms. Okay, now we have the following useful extension theorem. Suppose that X is a locally complex space, and X0 is a vector subspace of X. Then, for every continuous linear functional f0 on X0, there exists a continuous linear functional f on X, which extends X f0. So every continuous linear functional on a subspace can be extended to the whole space. The proof is almost the same as in the case of normed spaces. Maybe to make the proof more transparent, before I prove this, let's state our continuity criterion for linear operators in the special case of linear functionals. Well, now I see that it would be a good idea to attach numbers to our theorems. Let's do it. So the continuity criterion for seminorms, this will be theorem 1. Oops. Theorem 1. This will be theorem 2. And this is theorem 3. So a corollary from theorem 2 this is just a special case of theorem 2 for linear functionals. If X is a locally convex space and F is a linear functional of X. So we assume that P is a defining family of semi-norms on X. Then the following conditions are equivalent. F is continuous. Condition 2, the absolute value of F is continuous. And condition 3, the absolute value of F is dominated by finitely many semi-norms from P. So there exist finitely many semi-norms from P such that the absolute value of F is dominated by their maximum. So this is just a special case of theorem 2. Now we come back to theorem 3. Proof of theorem 3. So f0 is a continuous linear functional on x0. We combine this corollary with this observation, and we conclude that there exists a continuous semi-norm P. Well, maybe. Okay. There exists a continuous semi-norm P on X such that f0 of X is less or equal to P of X for every X in X0. Well, indeed, P is just this finite maximum multiplied by a suitable constant. And now we apply the Von extension theorem. So we have a linear functional on a subspace of a vector space satisfying this inequality. So the Von theorem implies that there exists a linear functional f defined everywhere on X, which extends f0 and satisfies the same inequality everywhere on X. And applying again this corollary, we'll conclude that this functional is continuous. Corollary implies that f is continuous. Okay, so every continuous linear functional defined on a subspace can be extended to the whole space. And as a corollary, we get the following result. If X is Hausdorff locally convex space, then for every non-zero element of X, there exists a linear functional f on X such that f of X is not equal to 0. And to prove this result, we first we define f on the one-dimensional subspace spanned by little x. And we define it as follows. Since x is Hausdorff and little x is not equal to 0, we see that there exists a continuous semi-norm P on X such that P of X is strictly positive. And now we define f0 on the one-dimensional space spanned by little x as a unique linear functional given by the following formula. So this equality obviously implies that for every point is one-dimensional space, Kx, the absolute value f0 of y is equal to p of y. So this corollary shows that f0 is continuous. To complete the proof, we apply theorem 3. And we get the, so we extend f0 to the whole space x, and we get a linear functional f satisfying this condition. So equivalently, this corollary can be stated as follows. If x is a Hausdorff locally convex space, the Hausdorff locally convex space, then for every pair of points x and y, such that x is not equal to y, there exists a continuous linear functional f, such that f of x is not equal to f of y. In other words, continuous linear functionals separate the points. This is immediate from corollary 1. We just apply corollary 1 to x minus 1. Of course, the assumption that x is Hausdorff is essential here, because if we have a non-Hausdorff topological space, then continuous functions can never separate the points. And the assumption that x is locally convex is also essential. So in conclusion, I'd like to give you the following example, or better counterexample. We take an arbitrary measure of space, x mu, and we take a number p strictly between 0 and 1. And we consider the legal p space, which is defined in exactly the same way as in the standard situation where p is greater than or equal to 1. So this is a set of equivalence classes of those measurable functions f, such that the absolute value of f to the power p is an integral. If p is greater than or equal to 1, then you probably know that this is a Banach space. But we are in a different situation. P is less than 1. Nevertheless, we can topologize this space as follows. For every f in the space, we consider the following number. We integrate the pth power of the modules of f over x. Of course, this is not a semi-norm because it is not homogeneous. Nevertheless, this semi-norm, this function determines symmetric by the following formula. This is an exercise for you. This is a metric on the big LP space. And if we group the big LP space with this metric, we get a topological vector space. For the topology generated by this metric. So it is an initializable topological vector space. But nevertheless, if, for example, x is the unit interval from 0 to 1, then the only continuous linear function on the space is identically 0. The dual space is trivial. So this example shows that the local convexity of x in corollary 2 is essential. This space is not locally convex. And as a result, there are no continuous linear functionals. The only continuous linear functional is identical 0. So, Theory 2 is, it illustrates the real advantage of locally convex spaces within the class of full topological vector spaces. This fact implies that there exists, we can construct a very rich and powerful duality theory for locally convex spaces, which simply doesn't exist in the case of arbitrary topological vector spaces. We'll discuss this duality theory maybe in the second half of our course. Okay, so that's all for today. At the next lecture, we discuss equivalent families of seminars, give some criteria, normability and metrizability criteria for locally convex spaces, and then begin to discuss some constructions on locally convex spaces, namely quotients, products, co-products, limits, and co-limits. Thank you.